Hi and welcome to this tutorial on percentage atom economy. In the previous tutorial, we looked at percentage yield and the relationship between the theoretical yield, so the maximum amount of product that you can get, and the actual yield, so what you got in reality. And we learned how to carry out equations and calculations involving it. So in this tutorial, we're going to be having a look at percentage atom economy. So a different thing, a different conceptual understanding of what's happening and why we need it. And we're going to look at calculations involving percentage atom economy as well. So atom economy is really important, like percentage yield as well, for chemical engineers, whether we're doing it for industry or for medicine. Really essential that we work out a good percentage atom economy. It saves money, it saves energy, fossil fuels, etc. And it's because with some of our reactions, we can get byproducts that are useless. Those might need to be disposed of in a complicated and expensive way. They might be harmful, or it's just wasting energy. So the byproducts, they are secondary products made using the synthesis during the synthesis of another product that we actually want. And really, as an engineer, we'd want to reduce the amount of byproducts made. And so the percentage atom economy is a way to measure how much of the reacting particles become the desired product of a reaction. So the desired product excludes all the byproducts, of course. So the relative molecular mass of the desired product divided by the total molecular mass of all reactants times 100. That is your equation. So MR of the desired, and we'll obviously do some calculations of this, total MR of all reactants times 100 is going to give you your answer. And most of the units we'll be working with are kilograms, grams, and moles. If you have reactants that combine to form a single product and nothing else, your atom economy is 100%, which is obviously very helpful. It means everything you make is going to be used and is desired. And the percentage atom economy for the reaction, it depends on the reaction. So as a chemical engineer, you might know that we could make something like, I'm making this up, but carbon dioxide could be made using multiple different types of reactions. And you need to weigh up, look at those different reactions and say, okay, well, the percentage atom economy of that one is higher than it is for this one. But that one uses more energy. It's all to do with compromises. And it is just distinctive to the particular reaction. It doesn't change. So it's always, with chemical engineers, it's always a playoff between the percentage yield, which we looked at in the last tutorial, and the percentage atom economy. So for example, the same reaction might have a 98% yield, percentage yields for the previous tutorial, in a professional industrial plant, but only a 30% yield in the classroom for various different reasons. But the percentage yield does not consider any byproducts. Okay, we're just looking at the product we make and how much compared to the theoretical and actual. Whereas the percentage atom economy is reaction based. It doesn't matter where you do that reaction, it won't change. Okay, it's a measure of how much the reactants in terms of mass is being converted into the desired product. And it does consider side products. So the percentage atom economy will be the same in an industrial plant as it is in the classroom. And the percentage yield tells you how wasteful the process is. The percentage atom economy tells you how wasteful the actual reaction is that you've picked out of all the options you might have. So a reaction might have a low atom economy. So if it produces little of the desired product in the equation, but it could still have 100% efficiency, so 100% percentage yield. A high percentage yield doesn't always mean the reaction is efficient. So these are two separate things that we're considering. So it means that the actual yield of the product is very close to the theoretical yield. That would be a high percentage yield. Okay, that would be like getting a very high score in an assessment. You got 97 out of 100. Your actual result is very close to the theoretical result. So this would still be true if the majority of the reactions form byproducts instead of the desired products. Okay, so it could be that although you've got a 97% yield, you're actually making quite a lot of useless, wasteful things that we don't want. So it's actually still relatively inefficient. The higher the percentage of the atom economy, the cheaper the process, of course. So the more of the desired product you're making, the less byproducts, wasteful byproducts you make, the cheaper the process. So here we've got a low atom economy, So we're making all sorts of different products here. Imagine I only want the blue circles. I'm also making some purple, some red, and some yellow. They're useless. They're going to go in the bin or somewhere that I don't need them. This is a high atom economy. The products I've made, they're all blue circles. I can use them all. So the higher the percentage atom economy, the greener the process is, because less waste is being produced. I don't have to worry about how to dispose of the byproducts and what I'm going to do with those. And they tend to be more sustainable because they use raw renewable materials. So that's why I've got this lovely sign here. And to calculate the percentage atom economy, you're going to use a reaction from the balanced equation. So you need to have the balanced equation. So I'm going to do a worked example. You can pause the video and give it a go yourself if you've already covered this before in a GCSE, for example. But otherwise, yeah, pause the video, give it a go yourself, or wait for me. First of all, I'm going to write out the relative molecular masses, the MR, of each of those. So the MR of my TiO2, my titanium oxide, is going to be 47.9 for the titanium. I got that from my periodic table, plus 16 times 2, because I've got 2 oxygen atoms. That's 79.9. And my MR of my magnesium is 24.3. And my AR, I guess that's AR of magnesium as well. My AR of the titanium is 47.9. Okay, so I've got my percentage atom economy. My calculation is slightly different. It's going to be the MR of desired product divided by the total MR of all reactants times 100. Okay, so my percentage atom economy is going to be my MR of my desired product. So I want the percentage atom economy for titanium. So that's just going to be 47.9, because that's my desired, divided by the total MR of all reactants. And remember, it's reactants, not products. So let's look at my reactants. I've got titanium oxide. I calculated that already. It was 79.9, plus magnesium. Now I've got 2 magnesiums. So it's going to be 2 times 24.3, because the AR of magnesium is 24.3. Okay, so I put that into my calculator. Of course, I'm going to times that by 100. And it's going to give me 37.3%. And that is your answer.